To talk about atmospheric composition and transport. And as pointed out earlier today, there are a variety of studies going on that are looking at research needs and capabilities of the observing system and the modeling system to look at various aspects of transport and chemistry. And we're going to have fruitful discussions this afternoon. So I'm not going to spend a lot of time summarizing these or talking about any specific processes, but rather talk about how we use these tools to try to look at problems of interest and try to illustrate some of the capabilities and some of the challenges that we have as we move forward. Clearly, much of the work in terms of modeling up to this point in time has been looking at trying to describe the total composition of the atmosphere and the impacts of the total composition. Now, through hemispheric transport and through climate change, we want to ask tougher questions of the models and want to know sensitivities of the response, and we want to be able to attribute source emission sectors over much larger geographical time. So in terms of the major pathways, Drew has talked through his presentation, has illustrated many of these transport pathways very nicely. This diagram comes from the National Academy report that just came out looking at the global sources of local pollution. So again, we understand, or at least we can characterize the large-scale transport processes, and it's just illustrated here. But from a chemical perspective, as we look at the short-term radiative forcers, such as aerosols and ozone, as those materials move through the atmosphere, we had complexity to that transport because we have chemical reactions, we have interactions with clouds, we have interactions with surfaces through removal processes. And so how those materials move through the atmosphere with these chemical and physical removal processes have an important role in terms of their spatial distribution. And when we look at radiative forcing of ozone, very important to be able to characterize the amount of ozone in the mid to upper troposphere and in specific regions. From an air quality perspective, we're more interested in driving that from what's happening at the surface. And so as we move through these processes, the aerosols and ozone also respond to those processes differently. So I'm going to use this diagram as I move through my talk here. It's really, think of it as the chain of calculations, and it's a simplified view of that. But we know, we've heard already about the emissions and how important those are. And again, in describing the total response of climate and the total impact of health and agricultural response, we need the total aerosol loading or the total amounts of ozone. But again, as we move forward to policy perspectives, we need to attribute that, which is a tougher problem. And then we move through chemical transport models, which give us the four-dimensional distributions, which then themselves are used for many impacts analysis, such as health. We then move up this chain. As we move, then we want to ask things about the interactions of those composition and the optical properties, in the case of aerosols, for example. Then we need to bring in further pieces of the analysis, radiative transfer models. We can use those to give us information on such metrics as direct radiative effects and forcing. And then ultimately, we want to move on, and as already illustrated in today's talk, we look at climate responses, and then we introduce added complexity through climate modeling systems. And again, these can be, I'm showing this as a chain of calculations, but they clearly can be highly coupled and embedded. And here, of course, the climate response gives us another set of metrics of impacts. And again, ultimately, from a policy perspective, and what we're trying to do as we move forward through a lot of these assessments and is to use these tools, in this case, modeling and observations, to really try to understand a change of some metric with respect to the emissions, and so then we can, again, that will give us guidance. And I want to point out that clearly models, the models really represent the entire community. It's not just the modeling community runs the model. It really represents our attempt as a community to put into these systems the complexity of the emissions we just heard, the complexity of the atmospheric chemistry and microphysics. And so they really do represent our best attempt to put in our understanding of those processes at play and then allow them to act through the system. And in terms of uncertainties, we can start at any part of this chain. So we've started at the emissions. And as we've heard, there's significant uncertainties in those emissions. And in general, those uncertainties are going to get larger as we move through the more complicated change, because we're adding processes that, in coupled ways, that we don't fully understand. At least we don't fully understand the process itself, and certainly how the processes respond in a highly coupled system. Let me use just some examples here to go through the models and the issues that we're always asking in terms of models as we move through a whole variety of not only models, but our observing system is readiness and capabilities to address specific problems. And certainly one way that we can test our understanding and add to our understanding of the processes that play in the atmosphere through large-scale field experiments. I'm going to talk just a couple slides here on one such experiment, a NASA INTEX-B experiment conducted in 2006 in the Eastern Pacific to look at a time period where there was transport from Asia into North America. And I think Kathy's going to talk in great detail of experiments focused on the Arctic. And again, so looking at this part of the chain is really looking at going to emissions to kind of this four-dimensional distribution of trace gases and aerosols. And if we look, these are the flight paths DC-8, and I'm just summarizing just very quickly here. We can compare the meteorology, predicted meteorology with the observed meteorology by the aircraft, summarized in terms of vertical profiles for all the flights. We can see that the model has appreciable skill in calculating meteorology, and that's no accident, because we have 50 years of designing observing systems that are used along with meteorological models to provide our best estimates of weather. And here are just examples of the ozone distribution. And again, we can see that very importantly from a radiative forcing perspective, we see in this region and everywhere that we have high ozone concentrations as we move up in the troposphere. And we see the differences between models and observations grow as we move up. And this slide simply shows a snapshot for that 1 month period of black carbon as it moves across the Pacific at 3 kilometers. And this shows ozone. And the point here is that these distributions in space and time look very different. And they look very different because of the processes at play in terms of removal and generation of those species. So here, again, during the INTEX-B experiment, there's a measurement operating at a mountain site, Mount Bachelor. This is the surface observation at the mountaintop. It's busy here, but if you look at the red dots, those are observed ozone, and the model calculated ozone is in black. But importantly, this is the model calculation of the vertical sounding of the vertical distributions over Mount Bachelor. This is ozone again, and if we look at the ozone distribution is synoptic, but also has large amounts of ozone in the column above the surface because of a variety of processes, including stratospheric tropospheric exchange. And so you see this large-scale structure, and dust, of course, coming from Asia was emitted at the surface, but as it is transported across the Pacific, is transported largely in the mid-troposphere, and then can be brought to the surface as the air masses reach the western parts of continents and then descend, mixing in with the boundary layer. And in dust, we can track that very carefully. But when ozone comes in, it gets mixed with more regional and local pollution, and it becomes very difficult to track ozone and its distribution as we come into a continent. So we have large uncertainties in how material as it reaches the continents descends. But what this also points out is that there's significant variability in the vertical, and it really poses challenges to our observing systems moving forward as we're trying to quantify and test and use observations to determine material above the surface. Well, the Himalayas is, through the ABC project, we're doing lots of work in Asia and setting up measurement sites and modeling. And certainly there's a lot of interest in climate change and pollution in the Asian area. And I'm going to show one slide here from the Himalayas. The Italians are operating the Pyramid site. It's a measurement site under ABC. It's located at the base station for the Nepalese assault to Mount Everest. The site is located here. You can see here it's at 5 kilometers altitude. It's an excellent site for measuring what's happening on the continent. And what we see here is ozone, but more importantly, also important is black carbon. And we can see from these black carbon measurements that in certain times of the year at this site, we can see pollution levels of black carbon reaching up at that altitude. And that is obviously very important from a impacts perspective, because this is really the third pole is really the water fountain of Asia. And that has profound implications for food and water security issues. Another experiment that we're doing has been done in ABC that we'll hear from Ram more tomorrow is measurements of the optical properties and vertical distributions of aerosols as they leave the Asian continent. And so here we can begin to take that for the distribution of aerosols that are calculated from emissions by the chemical transport model, and then begin to see through the vertical profiles and optical properties how well as we move one step along the chain in terms of those calculations. So here's some measurements by a new instrument by Flowers, looking at scattering and absorption. And my only point here is to point out that the observations are in black. The red is our best guess of the optical properties influenced by the observations in the literature. But there is variability in those optical properties that gives you a range of uncertainty that would come in that calculation. So there is still, there's capabilities in the models, but there's also severe deficiency that needs to be, or it's a source of uncertainty moving forward. So if we move one step further and then take the, then going from emissions now to estimates of the direct radiative effect or forcing, ABC is also doing that, and we've done a series of 5-year runs here that indicates the influence by the observations, 5-year run of, in this particular case, our model, using MM5 and WRF to drive our regional transport model, then through the Scripps radiative forcing calculation. And you can see here, this is the mean distribution dimming at the surface. This is the warming due to the atmospheric warming due to the absorbing aerosol. And these then are model calculations of the vertical distribution of the heating rates in Kelvin per day. And what's important here, if we look across, that got shifted, that should be across the India here, you can see that the heating rate is very strong above the surface. And that has critical information for helping us think about the response of the interactions with cloud, the overall forcing rate, as well as the dispersion of pollutants. We changed the stability structure of the atmosphere. And so these are significant, but point out that these estimates are highly uncertain when we compare to other model estimates. And so a lot of work needs to be done to try to quantify our ability to constrain the absorbing part of the aerosol. And I think right now our observing system capabilities and our instruments and our estimates of emissions and the models to do that is quite limited. But because of those strong forcing rates, it's very important to point out that we expect to have profound implications on meteorological and ultimately climate systems. And as Drew pointed out, looking at long-term trends of temperature, we need absolutely to have the aerosols into that analysis. And because of that reasoning, now we're finding that operationally meteorological services are moving more and more to including the aerosols into their operations and including those into their effects. And that's going to give us a lot more capability of understanding the processes moving forward and a lot more statistics to look at these effects. And this is just a result that we've been doing for the Beijing Olympics, which has been a very strong perturbation in terms of aerosol distributions using WRF Chem as a sensitivity experiment. And we can see through this slide some very large perturbations on stability, but also precipitation. Yeah. So finally, I'm going to skip this, but we are doing calculations of sectorial analysis, and that is really critical to link, again, more information from the emissions and using sectorial information from David Street's and Tammy's work and others, we can propagate that sectorial information forward and, again, giving us important information on the relative sources and sectors important for the transportation, for black carbon, for sulfate, for all of the different aerosols as well as the chemical species, and that again is very important. But again, I want to point out that this places increasing demands on the observing system and on the emissions and on the modeling, because we can take those emissions estimates by sectors, we can run them through models, but how can we test and verify that the relative importance of one sector or the absolute importance of one sector? Can we verify that from an observing system? And these slides show the relative contribution to the pyramid site from the relative sectors for black carbon and for sulfate. So finally, these indicate that we have a lot of capabilities, I think, in our understanding of these processes, and models try to attempt to represent that. And then I think that to many of these applications, they are in a state of readiness for guidance in terms of at least giving us the right direction, but they are very, very challenging because of the processes and other uncertainties in the emissions and all the other processes along the way. So the road forward, of course, is to try to come up with a better design and also a tighter integration of the various capabilities from our understanding from observing systems to emissions to, and I think that is very important. This was pointed out by the National Academy report. And just to give you one example of how this integration can really help, a recent paper by Uno, and I don't know how many saw this, was recently in Nature Geoscience, but what he was able to do was to piece together a global chemical transport model with a pretty high resolution meteorological model, as well as some assimilation in the dust source region, and combine it with Calypso data to actually look at a dust storm event that occurred in the Taklamakan region and follow it around the globe totally and another halfway around the globe, and looking at the Calypso and then going in and looking at the Calypso LiDAR tracks to be able to piece together a really astounding representation of following a plume across globally. And as we move forward over the next decade, I challenge us to see if we can do this with as our observing and modeling systems get better, can we follow these plumes farther and farther? Thank you.